So continue our discussion on the convolutional autoencoder. This is the code for a convolutional autoencoder, and this one also works for the facial MNIST. So you can see that. Okay, first, okay, we in the encoder, okay, we have this 28.1, okay, because now because we are using the convolutional layer, so we can deal with two-dimensional data. So we don't need to flatten that into like one-dimensional, okay. And we only have like one channel, okay. So so input shape is 28, okay. And then okay, we use COM2D, okay. We create like 16 feature map on top of this input, okay, with kernel size to be 3, okay, 3 by 3, padding to be the same, aggregation to be 0, okay. And then, okay, this one, okay, does not reduce the size, okay, even though the kernel size is 3, but because the padding is the same, so the size will be the same, okay. But in the next line, okay, we use max pooling, so the pore size is 2, so the width and the height both got to be cut by half, okay. So then we have another COM2D, okay, which creates 32 visual maps, okay, with this 3 by 3 kernel, and again same padding, 0 equation, and again we apply max pooling to further reduce the width and the height by half, and then okay have another COM2D. Okay, now we have 64 visual maps with 3 by 3 kernel, same padding, 0 equation, and again cut the width and height by half by max pooling. So at this moment, we are producing the coding, okay, here, okay. So now, okay, this is for the coding, and for the encoder, this is for the encoder. For decoder, okay, we use transpose convolutional layer. So we use COM2D transpose, okay, and so which is similar, but it's we use stride 2. So this stride 2 means we increase the width and the height. We double the width and the height. Okay. So in some sense, each of this line is the reverse of COM2D and max pooling. Okay. So we have 3 steps of this, right? COM2D max pooling, COM2D max pooling, COM2D max pooling. So we also have 3 COM2D transpose. Each one, the stride is 2. Okay, and so the feature map, okay, originally is 64. Okay, so this is like the coding. Okay, so once this one cut down to 32, and this cut down to 16. This cut down to 1. Which will, basically like convert it back to the original shape. And you can see here, okay, we still use the sigmoid aggregation. Okay, remember we still treat each pixel as a binary classifier. Okay, so this aggregation is sigmoid. Okay, and we reshape it to 28 by 28, so we get rid of that third dimension. And then, so this is a decoder. And then we combine encoder and decoder to form our convolutional autoencoder. Okay, that's it. Okay. Hopefully this is not too difficult to understand. Okay. And we can also have recurrent autoencoder. Okay. So say you want to build an autoencoder for sequences, such as time series or text. Okay. Then we could use recurrent autoencoder, okay, because recurrent neural networks, okay, will be better chaos.layers, LSTM 100, return sequence equal to true. Input shape is none, 28. This one, okay, oh, by the way, this example, still we are talking about Bayesian MNIST data set. Okay, we treat, remember Bayesian MNIST data set is 28 by 28, right? Okay, so we treat that 28 by 28 picture, okay, as 28 one-dimensional sequences. Okay, so that's why it's a non-28. The non stand for like we treat that dimension as a sequence. Okay, but 28, I mean, we have 28 such sequences. Okay, so so we have 100 neurons, recurrent LSTM neuron. Okay, and then we have 30 LSTM neuron. Okay, which works as a coding layer. And then here, okay, we try to use this repeat vector 28 equation 30. Okay, we try to create, because this one, okay, is going to, remember, for this one, there is no return sequence, okay, to set be true for the last line, for the last layer in the encoder. So this output is going to be just the last output, which is 30. Okay, it's only going to output 30 numbers for one picture, Okay, but here, okay, because we are going to use it for the recurrent layer, so the input will be expected to be a sequence. So this one is a repeat vector. Okay, this one we try to, what should I say, like we try to make this like 30 number, okay, as a sequence. Okay, we try to convert this one into a sequence. Okay, and then which will be used for this 100 LSTM neuron, okay, layer, okay, and then okay, we will send this output to the time distributed dense layer, okay, and we still use signal activation. We still treat each pixel as like a binary classifier, okay, and that's pretty much about it. So we have a recurrent encoder, recurrent decoder, and we combine them to be a recurrent autoencoder. What is special in this example is that we have a repeat vector. This particular statement, okay. So this one is a sequence to vector. This one is a vector to sequence. So if you ask me, okay, what kind of architecture is this autoencoder, autoencoder? It's going to be, I would say, it's going to be something like encoder-decoder network. Remember, we have 4 different RNN architecture, 4 commonly used RNN architecture. The last one is called encoder-decoder. Remember? Okay, so which can best describe this RNN autoencoder. Okay? I think I already finished like all this. Okay. So far, okay, all the autoencoder example that we have seen, okay, the coding layer, the dimensionality of the coding layer is lower than the dimensionality of the input layer. So remember, we call those that type of autoencoder as under complete autoencoder, right? But there are situations that like you know, we sometimes need to, you know, the coding layer sometimes need to be larger than the input layer. The dimension of the coding layer need to be larger than the input layer. Okay, if the autoencoder has such a property, we call it over-complete autoencoder. Okay, and you could imagine, okay, a lot of time, I mean, when you try to limit the dimensionality of the coding, is the reason is to create like a constraint, right? So that it can learn something from the input data, right? So why do we, I mean, in what situation do we need over-complete autoencoder? Obviously, I mean, if the autoencoder looks like that, okay, copying the data from the input to the output is not going to be an issue, right? It's not going to be an issue, right? I mean, it's there are other situations. For example, okay, one best example that we can talk about is like if your input has noise, and if you want to somehow remove the noise, okay, from your input, and somehow recreate a clean input in output, okay, in that situation, then you may need an over-complete autoencoder, because the constraint does not come from the architecture. It doesn't come from the structure of the autoencoder. It comes from the data itself. Okay, because the data is noisy. Okay, so the constraint is the noise in the content in the data. Okay. So the autoencoder that somehow like deal with the noise is called the denoising autoencoder. Okay, and so this idea, okay, to use like an autoencoder to remove noise, okay, it has been around for a long time. You can see since 1980s. Okay, but I probably should point out that the autoencoder was not invented until year 2000. No, after year 2000, I should say, after year 2000. Okay, so even before the autoencoder was invented, okay, such idea was already there. Okay, it was mentioned in Yang LeChong's 1987 master's thesis. So this guy is crazy, you know. Before autoencoder was invented, okay, he already envisioned, okay, such application. So in a 2008 paper, Haskell, Vincent, okay, this group, okay, showed autoencoder could also be used for visual extraction. Okay, in the 2010 paper, okay, Vincent, okay, the same set of also introduced step denoising autoencoder. So you can see that the real denoising autoencoder wasn't available until 2010. But when did Yang LeChong thought about this idea? 1987. So about like 20 years before this thing was invented. Okay, he already envisioned, okay, such thing. Well, okay, so that's why, remember, I mean, you know, previously when I talk about Yang LeChong's comment, I always tell you like, you know, this guy is something else. You know, you should, you know, if he gives some advice, you know, if he gives some comments, you know, you should take note for that. Okay, because he is a man came with a vision. Okay, he can see something that will happen 20 years, you know, in the making. So this guy is crazy. You know. Anyway, no wonder like Facebook hired him to be like a director for the AI research lab. But also, I think after he worked for the Facebook AI lab, I think research lab, I think you see we used to, a lot of people used to use carrots, but now a lot of people use PyTorch, right? So this thing is like, I think he also envisioned that to happen, when he started working for Facebook. So anyway, this guy is, I think Google didn't hire him. It's one of the biggest mistakes, okay, for Google. Okay. But anyway, okay, the noise can be pure Gaussian noise added to the input, or it can be randomly switched off input. Okay, so take a closer look at these two types of situation. So it could be Gaussian noise. It could be randomly switched off input. Okay, so how do we implement randomly switch off input? We just use dropout. Okay, because we know dropout, okay, will randomly switch off the couple of nodes, right? So, but remember, okay, we need not only we need the input with the noise, but also we need to know the noise-free input, because we want to use that as the label, right? Because okay, the autoencoder, okay, eventually when it gets the input, okay, it wants to produce the output that's resembling to the input, right? So what happens actually? Okay, you can see we intentionally add the Gaussian noise. Okay, we inject the Gaussian noise in the input. Okay, and then have the result to go through this. I'm sorry, the autoencoder. And because we do that, so obviously we know exactly what the original clean input is. And we are going to use this clean input as the ground truth to compare with with this output. Okay, same thing applied here. Okay, input, okay, is connected with the dropout layer. Okay, and then it goes through the hidden layers and then go to the output. So basically this dropout layer is going to randomly switch off some inputs during training. And the input, okay, is known. Okay, the input is known, so it will be used as the output, as a ground truth for the output, for comparison. Okay, so basically, okay, obviously this, no matter this situation or this situation, I mean, we know exactly the clean input is, okay, and the noise, no matter it's a Gaussian noise or dropout, they are intentionally added during training. Okay, during training. But after training, remember, for example, dropout. You guys know dropout after the training. Dropout only work during training, right? After training, like when you use it for inference, dropout layer will no longer, even though you have that in your model, but the dropout layer will not work. Okay, it will just it will not be activated. But anyway, so same thing. Okay, you could use, so this is the example, okay? You can see, this is dropout encoder, okay? So we have, we still use the facial NIST data set. So you can see flatten this image into one dimensional, and then we apply dropout with 0.5. 0.5 means what? Means you have, for each pixel has 50% chance to be dropped. So this is a very high drop rate, right? It's a very high dropping rate. So and then okay, we go through 100 neuron activation, dense layer, and the 30 neuron, okay, coding layer, and then okay, in the decoder, okay, we try to reconstruct the original input, okay, and then that's it. So if you want to implement the Gaussian noise layer, okay, then we use we can use a Gaussian noise layer, okay, and this Gaussian noise layer, okay, just like a dropout, okay, it only work during training. When you are using the model for inference, okay, this Gaussian noise layer will not function, okay, will not be functional, okay. So, which is nice because that's exactly what we want, okay. And then we combine this encoder decoder to form the dropout encoder. So this is nothing new, okay. So, so we can see in the figure on the next slide, okay, the image which gets dropped off, okay, for half of the pixels, and that input will be reconstructed by our denoising autoencoder. So you can see the top one will be the close. Well, this looks like a close, which are 50% of the pixels are dropped, and our autoencoder is able to reconstruct the original input. Same thing applies. I think this is like something like coat. Okay, this is T-shirt. This is long sleeve like dress and high heel. Okay, so you can see that. Okay, the image actually gets dropped very terribly, right? Okay, but still our autoencoder is able to reconstruct the original input. Okay, I mean, like, it's not like as clean as the clean input, but at least you can obviously still see what type of fashion item it is, right? So you can see that this denoising autoencoder is very good. And by the way, you can see that from here, you can also see that denoising autoencoder can be used for data imputation. Remember, in the sequence, in the time sequence data, we talk about there are two types of questions that we need to address. One is forecast, okay, the other one is imputation. Okay, we collect like a certain, for example, like a sensor input. Sometimes the sensors may not be functioning. Okay, so at some point of time, okay, I mean you may miss certain values. Okay, so what do we do? Okay, the input will be something just like here. Okay, you have some inputs, but you have some other inputs that are missing. So you could use the denoising autoencoder to reconstruct, to try to get those missing input back. Okay, which is like a complete practice for data imputation. Okay? So so that, okay, the denoising autoencoder is one of the over-complete autoencoder, okay? And there's another type of autoencoder called sparse autoencoder, okay? Sparsity, okay? By adding appropriate term to the cost function, the autoencoder is pushed to reduce the number of active neurons in the coding layer. Okay? For example, it may be pushed to have on average only 5% significantly active neurons in the coding layer. So only 5% of the neurons in the coding layer will be active. Okay? So that's like what we want to achieve. Okay? So this forces the autoencoder to represent each input as a combination of a small number of activations. Okay? So what does that bring to us? I mean, what's the benefit of that? Okay? Normally, okay, if you do that, okay, each neuron in the coding layer will typically end up representing a useful feature. Okay? So you can, in some sense, remember, because sometimes you want to explain your data set into some meaningful way, right? But sometimes it's difficult to do that. Okay, this falls into a category of the what we call explainable AI. I don't know if you know about this area. Okay, it's called XAI. That X stands for explainable. Okay, explainable AI. So if you want, I mean, you can use this to try to achieve like this goal. Okay, basically like try to explain, okay, what this data, okay, what certain feature this data, represent, okay, by using like the combination of the activated neuron in the coding layer, okay. So the idea is like this: if you could speak only a few words per month, you will probably try to make them worth listening to. So you will try to be very selective and try to only, talk about very informative, like the words. Okay, so this is something like that. Okay, so how do we achieve the sparse autoencoder? There are a couple of ways to do that. Okay, an easy way, a simple approach, okay, is to use a sigmoid activation function in the coding layer, okay, and add L1 regularization to the coding layer activation, okay. So basically, okay, the biggest, reason for this autoencoder to be sparse is because you are using L1 regularization. Okay, so what happens? That's a loop. Okay, so we call this sparse L1 encoder. Okay, so again, we try to here we are still using the measured anonymized data set. Okay, so you can see we flattened the 28 by 28 image into one dimension, and then okay, we have it go through hidden layer. Sorry, the dense layer is 100 neuron. Okay, zero activation, and then we have it to go through 300 neuron dense layer with sigmoid activation. Be very careful. Okay, you can see from 100 to 300. This is the coding layer. So that's why, okay, I say this is in a sparse autoencoder. Normally, because we want to achieve sparsity, so normally the middle layer, the coding layer, has more neurons than the other layers. So you can see the middle layer 300, the previous layer is 100. Okay, so you can see after this dense layer, okay, we intentionally add the activity regularization okay, L1 equal to 1e minus 3, okay, 10 to the power of minus 3. Okay, so we try to put a regularization to constrain the activity for the coding layer. And the sparse L1 decoder, I mean, this part will be, there's not pretty much nothing to talk about, okay? So you just, you get, from 300, like output, you try to, you have 100 neurons with the C regulation, and then the other part will be the same as the previous one. And then you combine encoder and decoder for autoencoder. That's it. So this is like an easy way to achieve sparse autoencoder. But, okay, so I already explained, what we have here, so I will skip that, okay? But there's another way to achieve that. Okay? Another approach, okay, which will normally yield better results, okay, is to measure the actual sparsity of the coding layer at each training iteration, and to penalize the model when the measured sparsity differs from the target sparsity. So here we are trying to measure the frequency of the activation for each neuron in the coding layer. Okay, so if the frequency of activation for a neuron, okay, is different from the target sparsity too much, we'll penalize this model basically. Okay, so we do so by comparing the average activation of each neuron in the coding layer over the whole training batch. This training batch needs to be, slightly bigger, so that this computation of the average activation of each neuron to be representative. Okay, otherwise, if the batch is too small, then each neuron may, its average activation may not be very accurate. Okay, may not be very representative. Okay, so the batch size must not be too small, or else the mean will not be accurate. Okay. So once we have the mean activation per neuron, okay, we will penalize the neuron that are too active or not active enough. So why is this approach better? Because the previous approach, this approach, okay, we try to only calculate the activity, the active neurons for the whole layer. Let's say if you want like a 5% activation, okay, then what happens like if you have like 300 neurons in the middle, okay, maybe we have on average 50 neurons to be active, right? That's 5%, right? Okay, 15 out of 300, right? Okay, that's 5%. But the issue is that 15 neurons, okay, the 15 active neurons may happen to be active every time. Okay, so that's it. This class is the coding layer. Okay, and each time maybe, okay, only if you measure the sparsity of the whole layer, maybe each time, for each iteration, there's only 2 neurons that's active. But in reality, maybe those 2 neurons or those 2 people, maybe me and you, maybe only 2 of us that we are active. For every iteration, all the other people are dead. But we don't want that to happen. We want that 5% sparsity to happen for every neuron. So every neuron will be only active for 5% of the time. Something like that. So this is a little bit different from what this one can bring to us, right? Okay, so that's why the second approach is slightly better. Okay. So we already talked about how to measure the sparsity, but how to penalize, how to okay. Once we have the mean activation per neuron, okay, so we want to penalize the neuron that are too active or not active enough, right? So by adding a sparsity loss to the cost function, okay. So if we measure that, say we measure the neuron, okay, the neuron has an average activation of 0.3, but the target sparsity is 0.1, so 10%. But this neuron is active, is active like for 30% of time. Okay, so it's too active. Okay, so it must be penalized by active less, right? So one approach, we just adding the square error to the cost function. Okay, 0.3 minus 0.1 to a power of 2. So this is easy, right? But in practice, a better approach is to use callback library divergence. I don't know if you know about this KL divergence. Okay, KL divergence actually was covered in this textbook in chapter 4. Let's just assume this is a function. Okay, normally it's abbreviated as KL divergence. I will explain what this function normally is used for later. Okay, later. Okay, so let's just assume this KL divergence as a function. Okay, so this provides a stronger gradient than the mean square error. Okay, so here, okay, you can see the mean square error. Okay, no matter it's a green dotted line or a red dotted line. Okay, you can see the gradient. Okay, sorry, the green dotted line is the MAE, mean absolute error. Okay, so it's like this. Okay, it's a straight line. Okay, MSE is like this. So the gradient is the slope, right? So you can see the slope. Well, the MSE is slightly better than the MAE, right? But the KL divergence is represented by a solid blue line. You can see that the gradient of this solid blue line is much bigger than the other two, right? Okay, so that's why, okay, we normally prefer to use KL divergence for this for this situation. Okay, so the KL divergence is defined like this. Okay, I will not go into the detail. Okay, so we can use this. We just compute like the kind of divergence between the target sparsity P and the actual sparsity P is like this. You can calculate like this. But of course, we use the KL divergence, as a cost function here. Okay, as part of the cost function. Okay, but you may wonder, okay, what is like the normal application, okay, the common application of this KL divergence? Because when a function has a name attached to it, it must be an important thing, right? Okay. See, even the MSE, mean square error, doesn't have a name to it, right? Okay. So why do we call KL divergence? That callback library, okay? Not only one person, we have two people's names on top of this function. So what is the common application of this function? Okay, let me put it this way. Sometimes you want to measure how similar two distribution are. Okay, there's one distribution that goes like this. This is another distribution goes like that. Okay, it doesn't matter how, how it looks like. Okay, of course, if you want to measure it visually, if you want to measure the difference of two distributions visually, of course you could just look at the graph, look at the figure, right? Okay, but if you want to describe the difference quantitatively, okay, how do we do it? Scale damages. This is an important tool to know that you need to remember. Okay, I mean, a lot of things could be explained as distribution. Here, when I say distribution, I'm talking about a probability distribution. Okay, but I mean, when you see some distribution, I mean, they do not necessarily need to be a probability distribution. You know, probability distribution need to be like a the integral need to be one, right? Okay, the integration, okay, for for the whole defined region need to be one, right? That's the probability distribution, right? But the KO damages does not necessarily need to be applied to the probability distribution. Or put it another way, okay, the distribution could be two distributions could be explained as probability distribution in a much more relaxed manner. Okay, for example, okay, let me give you one example. Okay, this is like actually used in one of my students' thesis. Okay, sometimes you want to compare the activity or the pose of two people, right? For example, in a traffic, if you want to do some task for autonomous driving, okay, the car need to be able to recognize the gesture of the traffic police, right? Traffic police give you like this. You know what it is, right? Stop, right? So if it's autonomous driving vehicle, it needs to recognize this gesture and then stop, right? It cannot run over the policeman, right? Okay, so I mean, so how do we recognize the gesture, the policeman's gesture? Okay, one way to do that is like this. Okay, so you have the input video from a police, from a policeman's gesture, okay, which you shoot, you obtain from real time, and you have some video that you already stored for a certain police gestures. Okay, one of them obviously is stop. Okay, and what happens you could open pose. Do you know open pose? Open pose. We didn't talk about open pose in the CNN chapter, but the open pose is a model which will return to the backbone of your body. Okay, so it will give you key points for your body. For example, if the person is okay, so it will give you, for example, your eyes and your neck and your elbow, your hand. Or it will give you certain points, and then your chest, and then your, this point. Okay, so the open pose is going to give you these points. And then from this point, you can compute the angle. Okay, for each set of 3 points, you can compute the angle. Okay, and then you try to compute the angle of the input police gesture and the angle of the police stop video that you already saw. And then you just, of course, because you are shooting this video at real time, so you are going to get many frames, right? Get many frames. Each frame you are going to compute one angle, right? So you're going to get many angles. So you can treat these angles, the change of angles, as a distribution. Okay, and compare that to the video, the angle you obtain from the change of angles you obtain from the stored video. How do we compare these two distributions? K of divergence. And if two distributions are similar, then this K of divergence is going to return you something close to 0. If they are very different, it's going to return you a large number. Okay, so this can be used to measure similarity between something. Okay, it can be even used to measure similarity between two poses. Okay, so there are many applications of this callback library of divergence. Okay, so running out of time, but that's one. I think we'll stop here today. Next time we'll start from here. Okay, hopefully we'll finish the discussion of autoencoder and hopefully talk a little bit about the game. Okay, next time. Okay, any question? Next week will be the last lecture for this class. Okay, next week will be the 30th, right? Okay, the 30th. So the week after the next will be the final exam. Okay, as I have told you guys. Okay, well, the final exam is going to be held like a week prior to the final exam week, and we will have like the final project presentation in the final week. Okay? Just want to remind you again about that. Okay? Any question? Okay, if no question, that's it for today. So we will continue our discussion on the sparse autoencoder next time. Okay? Thank you.